Number 22. Many nuclides with atomic numbers greater than 83 decay by processes such as electron emission. Explain the observation that the emissions from these unstable nuclides also normally indicate or include alpha particles. Okay, so we're talking about nuclides with atomic numbers greater than 83. So we're only working with a select few isotopes here, right? So I'm just, cruising across the periodic table, looking for, an atomic number greater than 83. I guess we'll go one over, and we'll talk about atomic number 84, which is polonium, which is PO. Now, PO on the periodic table, on my periodic table, it says that it has roughly a atomic mass of 209. I guess we'll do 210 because I like even numbers. They're easier to work with, I think. So we'll take a standard isotope. We'll say we have a polonium 210, and the atomic number is an 84. And we're in the range, right? Because we just have to have an atomic number that's greater than 83. Remember that atomic numbers are always the number of protons. So, in this example right here that we just made up, right, we have a 210 mass number and a 84 atomic number. So let's just write that out. So let's bring this a little bit over here, and let's say that the top number is the atomic mass, or you could say it's the mass number. It doesn't matter to me. And the bottom number is the atomic number. Okay. So because of that, the atomic number is always the number of protons. So in this case, we know that we definitely have 84 protons. So let's just write that out. We got 84 protons because that's the atomic number. It's the number of protons. And then let's just find out the number of neutrons, because generally with stability and instability nuclides, it's always talking between the protons and the neutrons, because those are the two subatomic particles in the nucleus. And that is what the mass number is. A mass number is the combination of how many protons and how many neutrons you have. So in this case, we know that we have a total of 210 protons and neutrons, with 84 of them being protons. So what would I have to do to this number to, find my neutrons? Yeah, we just subtract, right? So if we do 210 minus 84, what would that be? Let's see. I do a little weird subtraction. 2 minus 0 is 2. 1 minus 8 is a negative 7. And then 0 minus 4 is a negative 4. Oh boy. This is a little bit crazy. So 20 minus 7 is 13. 30 minus 4 is 26. So I believe that this is going to be 126. Did I make that way too harder for myself? Let's see. If I do, we're just going to go backwards. Now, you might be watching me and like, what is going on? Yeah, or you could just plug it into the calculator. But let's see. If I do 126, do I get 210? 4 plus 6 is 10, so that gets me the 0. 8 plus 2 is 10, plus that 1 is 1. So yeah, okay, 126. Wow. Good job, Christina. All right, so we got 84 protons and 126 neutrons for that polonium. So if we go to our band of stability here, just to kind of show you what we're doing here, keep in mind that this blue band is the band of stability. There's only a few stable, atoms out there. All the green stuff, whether you're above the band of stability or below the band of stability, you're going to be unstable. And generally, you're going to be radioactive, and you will emit particles to make yourself more stable. Now, for where we are, right, number of protons, we got 84. So maybe we're like right over here. And we got to cross this with 126 neutrons. So I'm just going to put like a line up here. Let's see. Somewhere around here. And then 126. So maybe right here. Okay. Now we're 1 over because anything that's greater than 83 is automatically classified as radioactive. So I actually drew my thing good. But now let's see what happens when we emit a alpha particle. Now, emission means that you're throwing that particle into the products or into the atmosphere. If you're emitting something, you're throwing it out there for everyone to see. So that means that your particle is going to be on the product side. Now, just know that an alpha particle is the same thing as an helium atom. So I'm going to be breaking it off into an alpha particle, which is essentially a helium. So helium, right, if we look on the periodic table, helium always has an atomic number of 2. So 2 on the bottom, and we got a 4 on top. There you go. But now, that's the alpha particle. Let's see who is the daughter nuclide. The daughter nuclide is whoever you're turning into after you emit some type of radioactive material, right? Or your particles. So, keep in mind that the top numbers on the product side have to equal the top numbers on the reactant side as a total, and the bottom numbers as well. So if you have a total of 84 on the left side, what plus 2 will get me 84? Yeah, this has to be 82. 82 plus 2 is a total of 84. And then what's going to happen to my top number? 210 equals what plus 4? Well, I just have to basically subtract 4 from this, right? So this would be 206. And then always know that your atomic number is who the atom is. So as I'm looking on the periodic table, big lead is 84, always. Now, if we track where this guy is, let's see where we're at. We're now at 82, so maybe we're like over here, and 206. So 206, actually, just kidding, we have to do the protons and the neutrons. Were you screaming at me? Yeah, I heard you. 82 protons, because that's the bottom number, and we subtract these two, right, to get the number of neutrons. We have 2, 0 minus 8 is a negative 8, and then 6 minus 2 is a 4, so 20 minus 8 is 120, so we got 124. 124, let's put that down, 124 neutrons. Right? 20 minus 8 is 120. Yeah, 124. Okay. So now I'm going to see where this is. 82 and 124. So 82. Maybe we'll make a line up here. Autocorrect. Thank you very much. Gotta love autocorrect, right? Whew. Okay. And then 124 would be roughly around... actually here... This is actually a stable isotope. So this one is a really good example of why, explain how the emissions of those unstable nuclides also normally include alpha particles. Well, the main reason is that you're dropping down your protons and neutrons to make it into a stable nuclide. This is a stable nuclide. Now, the one other thing, IDE, the one other thing is that since you are decreasing, you're decreasing your atomic mass by 2 and the atomic number by 2, actually, you're decreasing your atomic mass by 4 because the 4 goes to the helium and the 2 goes to the helium as well. So you're decreasing your atomic mass by 4, 210 to 206, and atomic number by 2, 84 to 82. And because you're doing this, there's something called an NP ratio. And what's happening is you are increasing your NP ratio. And NP ratio is your neutrons to proton ratio. And if we do set this up, chances are this one is going to be a larger ratio. The majority is that generally if you are in a radioactive material that's low on the board, and you could always emit an alpha particle to bring that ratio up, that's what's happening here. So for any time that you have radioactivity that's below your band of stability, you will always emit an alpha particle because it will bring up your N to P ratio, your neutron to proton ratio. Decreasing atomic mass by 4, atomic mass by 2, increasing your NP ratio, which gets the daughter nuclide, which is the one that you produce. They just call it a daughter, right? Kind of like daughter cells in biology, which gets the daughter nuclide closer to the band of stability. So that's basically the majority of what's going on. Generally, if these, radioactive material is going to emit an alpha particle, chances are that their N to P ratio is way too low. And by emitting an alpha particle, always will increase that ratio. And by increasing the ratio, it will lead you to a closer band of stability. So like something up, something over here, alpha emission will always bring it up. And I hope this makes sense. And then in other cases like ours, it will, turn you into a stable nuclide anyway. So yeah, what'd you think? I hope this helped. Thank you so much for viewing the video. Subscribe to the channel if you haven't already. Thank you so much for your support. We just opened memberships if you want to become a member. But yeah, I hope you're having a great day. Keep studying hard, and I'll talk to you soon, okay? All right, bye-bye.